Good evening. This is Ifeanyi Roland Onyewaku, and today I'll talk about my Malthus population model with disease death rate consideration, my final report. As we know, this experiment was performed by Anubhav Pratap Singh to show Malthus's population model with disease death rate consideration. And this paper is being reviewed by myself and to make the model which was introduced here more efficient. So in this paper, he talked about the three different ways to predict population sizes, which is Malthus's, logistic, and coalition. However, we'll focus on Malthus's. And in this case, he also mentioned like 4 factors whereby man must eat to survive. The rate of population growth is always higher than the food production rate. There are consequences of these rates. The consequences of these rates needs to be kept equal. And then there's a decrease in population due to diseases, famine, poverty, and war. However, when he was calculating this model of implementing it, he only put into consideration time and relative growth rate. So hence, the solution we proposed was to introduce another parameter called disease-induced death rate. Now, what method did we use to implement this model? We previously wanted to use NetLogo. However, it kept crashing when we're implementing this model. We'll go into that later. Hence, we use Microsoft Excel. The agents are definitely you reproduce humans and you check death rate. The check death rate. Reproduce humans literally uses the birth growth rate. And the assumptions we made is each tick, when we're using that logo, is each tick represents a year and their maximum of 10 ticks, whereby if the initial population size would be that of 2010 and to run to 2020. The disease-induced rate generated from data from the CDC, which we'll show later, and then the disease will also be introduced in a year. Now, this is the previous formula which he had. He had like PT equals P's initial population times times E raised to power ampered times T, whereby PT is population time at time T, PO is initial population, E is of course 2.718, time is the A index, whereby 2010 is 0, 2011 is 1, the ampersand is the constant growth rate. Now we adjusted this formula and we added like the B, which is B on here, which is the percentage death rate as induced by diseases, whereby the final formula we put in is PO bracket E raised to power ampered times T minus the B. Okay, so now when we wanted to do this solution and simulate it, we had to get the information. When we went to CDC, we got the top 3 in the year 2010, which is heart diseases, cancer, and chronic respiratory disease. And when you add all these 3 together, it gives you 1.2 million deaths. And then, of course, the total living in 2010 was 308.7 million. To calculate the percentage death rate, we did the total death rate over total death rate plus total living, and that gave us approximately 0.39% death rate. Then the growth rate, which we got from Wiki, is basically 9.7% growth rate, and if you divide that over 10 years, which is what they use, you get approximately 0.0097, which is literally 0.97% per year. That's the increase per year. So now let's go. When we put in this calculation, of course, P was 2010. It originally, if you can look at in this graph, whereby this is a straight line, you can see it started matching a little bit. P1 was 310. Y estimated Y real was 311. For P2 2012, you see 313 million approximately. The next one's 360 million, 319, 318. The estimated and the real population was going together until the margins started increasing, whereby estimated population was going higher because it was just going straight. If we had inputted if we had put in like a check for another disease, like let's say Ebola, coronavirus, that's how it came in, I'm pretty sure it would have affected this. It would affect the population and drop it down, and it to keep going, and it to look more like the real population. Now, of course, the final results of our model looked great. However, when compared to the real world population, we can see that there's still like some differences, right? And meaning we need more investigation and modification of this model to make it much more efficient. However, we believe this model is more efficient than the one that was introduced in the paper. Now we got an issue. We had a problem using net logo because it kept crashing and giving the error below. This was my first time seeing it, so we just ended up using uh what's the name Excel, whereby we put in the you can see we put in the formula, the new formula on here, and we used that to make the calculation, and that's how we got our visualization. So thank you so much. I want to really thank Dr. Don Martin. He really gave a great teach and made us understand how to simulate data, population, illnesses, a whole bunch of data out there. This was a great class for me. I learned a lot, learned a bunch of tools that I never knew existed. Um, Thank you very much.